This is question number 2 from worksheet number 4 that we assigned on Monday. You've got a 1,500 kilogram car traveling west at 90 kilometers per hour, colliding with a 1,400 kilogram truck traveling north at 72 kilometers per hour. The entangle they head off is 1. We want to find the final velocity of the wreckage after the collision. We have kilometers per hour here in both our initial velocities. Does that matter? No, in the end, we can use kilometers per hour if we want, as long as we're consistent through the whole problem. Units in these conservation of momentum problems end up canceling each other out. I'm going to leave it as kilometers per hour here. Let's draw a picture. It's a two-dimensional problem. We always draw a picture. We've got to write down our givens anyways. We might as well draw a picture and write down our givens that way. We have this 1,500 kilogram truck, or car, sorry. We're going to call object number 1, going to the west. And then we have this 1,400 kilogram truck traveling north, going like this. We'll call that object number 2, label it as 1,400 kilograms, and a velocity of 72 kilometers per hour. Where are they going to go? Well, if we have a north momentum and a west momentum before the collision, then we have to have a north momentum and a west momentum after the collision. Somewhere north and west. Where exactly, we're not sure. Now we've got to break this up into x and y components. Do pi is equal to pf for both of those. We're going to say m1 v1 I, it's 1,500 times neg 90, plus 0. Why 0? This guy has no x momentum. It's moving on the y-axis, but we're not paying any attention to the y-axis here as we look at only the x component. So it's 0. The final momentum is m total times vf. Now we sub in our numbers here. We got 1,500 kilograms for the initial mass. For the first mass, we have negative 90 kilometers per hour, or we could have converted that to meters per second, equals the total mass is 2,900 kilograms times VF. If we solve for VF here, we end up getting a value of negative 46.55172, and because we use kilometers per hour for the initial velocity of object number 1, we get kilometers per hour for the final velocity here as well. We're not done though. We've got to do a y component. Same idea, pi is equal to pf, but this time object number 1 is the one with no momentum. It's got momentum on the x-axis, but 0 momentum on the y-axis. Plus m2 v2i, that's got momentum on the y-axis now because it's moving upwards, is equal to mass total times vf. Sub in our numbers for this one now. We got 1,400 kilograms times my initial velocity of 72 kilometers per hour. The total mass is once again 2,900 kilograms times vf. Solve for VF here, and the y component of the final velocity works out to be positive 34.75862 kilometers per hour. So neither one of those are my final answer, but I'm well on my way here. Now I got to combine these in the old physics 20 way of combining vectors. We have 46 kilometers per hour this way. We know it's to the left because it's negative. We have 34 kilometers per hour, or 34.75862 kilometers per hour this way. We know it's positive, therefore it's to the north. The resultant vector, which is really what we're trying to find here, is going somewhere north and west as we predicted in the original diagram. Solve for theta there as well. Get the value of v by using the Pythagorean theorem, 34.75862 squared plus 46.55172 squared. Square root that. And we end up getting two significant digits, 58 kilometers per hour. And we're going to solve for theta using the inverse tan function as we always do. Inverse tan of opposite over adjacent, 34.75862 divided by the adjacent side, 46.55172 equals, to two significant figures, 37 degrees. And we're going to write that as 37 degrees north of west because we're measuring the angle from the west, but yet we're going north from the west. 58 kilometers per hour, 37 degrees north of west. Now I would like you to, at your desks, take a look at worksheet number 4, question number 3. All right, let's have a peek at question number 3. 4-kilogram ball traveling north with a momentum, not a velocity, but a momentum of 11.2 collides with a 6-kilogram ball traveling west, again with a momentum of 18. The two balls stick together and head off as one. What's the momentum of the combined masses? What's the velocity of the combined masses? And what was the momentum of the system before the collision? All right, let's draw a picture. That's what we do. We have a 4-kilogram ball going north. We'll call that object number 1, with a mass of 4 kilogram, with a momentum, not a velocity, a momentum of 11 kilograms meters per second. We have another ball traveling west. We'll call that object number 2. Has a mass of 6.0 kilograms, and it has a momentum, once again, of 18 kilograms meters per second. And of course, they're going to go up this way somewhere after the collision, because we know if we have north momentum and west momentum before, we have to have north momentum and west momentum after. Listen, even though we have momentum here as opposed to velocities, we're going to tackle this in more or less the same way. The x component says pi is equal to pf. We're going to say 0, because object number 1 has only y momentum, no x, plus, now we could say m2v2i, but we already know what m2v2i is for the x component. It's 18, or we'll say negative 18. So instead of writing mv, when we know the value of mv, just write the number down. Negative 18 because it's to the left. Equals, we're just going to say pf. We're looking for the final momentum x component and y component, then combined. So let's get the final momentum x component first. It ends up being negative 18 kilograms meters per second. You could have taken this number, divided it by mass to get the velocity, and then turned around and wrote in mv right here, and then multiplied the two together. But guess what you would have got? 18. So we might as well just write in the value for momentum when we have it. Let's take a look at the y component now. We'll say pi is equal to pf again. This time object number 1 has a momentum. We know it's 11.2 kilograms meters per second. It's m times v, but we already have the value of m times v. Object number 2 is only on the x-axis, so we'll say its y momentum is 0. Pf is equal to, for the y component, 11.2. Now let's combine them. Our x component is negative 18. Our y component here is 11.2. And of course, the hypotenuse of that right angle triangle this time is not the final velocity, because we're adding momentum vectors. It's going to be our final momentum. We solve for it in the same way, though, using the Pythagorean theorem. Okay, it's equal to the square root of 11.2 squared plus 18 squared. Gives us a value for the magnitude of the momentum of 21.2 kilograms meters per second. And theta, we're going to say, is, of course, the inverse tan function of opposite over adjacent. It gives us an angle of 31.9 degrees. And we're going to express that north of west. North of west, because once again, we're measuring it from the west, but we're going north from the west. 31 degrees north from west, or north of west. Now, we answered the first part of this question. Let's go to the third part. We'll come back to the second part. What was the momentum of the system before the collision? We just found the momentum after. What's the momentum before the collision? Well, if this is the momentum before, then the momentum after the collision is exactly the same, because the law of conservation of momentum says so. The initial momentum is going to be equal to the final momentum. So there you go. We just found it without having to do another calculation. Now, what about the velocity? We want to find the velocity here. Well, we've got the momentum. Why don't we just say now p is equal to m times v, or v is equal to p over m. We got 21.2 at 31.9 degrees over the mass here. which is 10 kilograms, which gives us a velocity of 2.12 meters per second at 31.9 degrees north of west. That's it. We're going to have a look at example number 2 now that appears in the example booklet that I gave you on the first day of class. This one's a little bit different, similar but different. It says a 3-kilogram bundle of fireworks sitting on a table explodes into 3 pieces. First piece is 1.2 kilograms, goes north. Second piece goes 100 meters per second, 30 degrees south of east. With what velocity does the third piece head off? We got a couple different directions here, north and south of east. It's a 2-dimensional problem. We got to draw a diagram. We're going to say our explosion point is right here. This is what it looks like before the explosion takes place. Everything is in one place. Now, after the explosion takes place, we get a piece going up this way, has a mass of 1.2 kilograms, a velocity of 120 meters per second. We have a piece going at south of east, 30 degrees south of east. Its mass is 1.10 kilograms, and its velocity is 100 meters per second. We'll predict that the third piece is going to go over here somewhere. Now, could go up and left, down and left. We're not sure. We know it goes left, but we just don't know whether it's up and left or down and left. In the end, if we guessed wrong here, it doesn't really matter. This is more meant for us to visualize what's going on anyways. Okay, let's go to the x components and y components as we usually do. Pi is equal to Pf. Is there anything you notice here that we probably should do before we do x and y components? Yes, we have a funny angle here, 30 degrees. And of course, when we see that, we say 5 words, I don't like funny angles. So we draw it off to the side and we get rid of it. Got 30 degrees right here. We have 100 meters per second. We have an x component. And we have a y component. We can find the x component by cosine, because it's the adjacent side. Cosine 30 degrees is equal to x over 100. X ends up being equal to 86.6025 meters per second. And the y component is found by using the sine function, sine 30 degrees equal to y over 100. That's going to be equal to exactly 50. Just kind of box this off so it's off to the side where it belongs. Let's go back to our x component here. We're going to say object number 1 has 0, well, the whole thing has 0 momentum before the explosion takes place. It's a bundle of fireworks sitting on a table at rest. 0 initial momentum equals object number 1 has 0 momentum x component. It's got a y component because it's moving upwards, but no x. Plus, now watch carefully here. This is m1 v1f plus m2 v2f plus m3 v3f for the third piece. M2 is 1.10 kilograms. V2f is not 100. V2f is this value. We just broke down that 100 into an x and a y, and the 86.6025 was the x part of that 100. Once we break down that 100 into x and y components, we never use this again. It's dead to us. We're now using only the 86 and the 50. M3, we know by subtraction here that it has a mass of 0.70 kilograms. We'll solve for V3F there. When we do the math here, it works out to be negative 136.0896 meters per second. We'll do the same thing for the y component. Once again, the initial momentum is 0. This time we're going to say m1 v1f because object number 1 is moving on the y-axis. Object number 2 is as well, as is object number 3. Can't cancel with the masses because they're not the same. M1, 1.20 times 120, the y component of the 120 is 120, plus 1.10, watch this one. V2F is not 100, V2F is negative 50. 50 because that was the y component of the 100, negative because it's going downwards. M3, once again, 0.70 kilograms. It's the amount of mass that's left over. There's V3F. Solve for V3F here, and it's going to work out to be negative 127.1429 meters per second. Now, the only thing that makes this question different than the other questions we've done so far is this. In those right-angled questions, you had the value of the x component and the y component already. Here, we had to find the x component and the y component over here by breaking down the 100 meters per second vector. Now, at this point, it's exactly the same. We have a vector that is 136 this way to the left. We know that because it's negative value, 136.0896. We have another one that's 127 this way. Sorry, that one should be, it's a negative value as well, so it should be down. And of course, we solve for the resultant vector. Looks like that prediction that we made for the resultant vector was correct. It is left and down. Solve for v, solve for theta. Using the Pythagorean theorem, this works out to be 1.9 times 10 to the 2 meters per second. And theta, using the inverse tan of opposite over adjacent, gives me a value of 43 degrees. And this would be south of west. South of west because we're measuring our angle from the west, but yet we're going south from the west, or south of west. I'd like you to have a look at questions 4 to 6 now on worksheet number 4 at your desks. Last one for the day, example number 3. The same example sheet that I gave you at the first day of class. There's a 19.5 kilogram red curling rock heading north, collides off center with a 19.5 kilogram blue curling rock at rest. Red curling rock goes this way. It's the velocity of the blue curling rock immediately after the collision. We have a couple of different directions here. We have a north, collides off center. We get a west of north here. Looks like a what we call a glancing collision, where we have vector components here. Good news though, all of our masses have the same mass, 19.5 kilogram red rock and blue rock. Let's draw this out here. Object number 1 has a mass of 4.5 kilograms, mass of 19.5, sorry, a mass of 19.5, a velocity of 4.5 meters per second. Heading north, collides with object number 2 that's initially at rest. After the collision, object number 2 goes off this way, and object number 1 goes off this way with a velocity of 3 meters per second at an angle of 30 degrees. We're trying to find V2. Got a 30-degree funny angle. We know what to do here, right? I don't like funny angles. So we take it off to the side, and we're going to get rid of it. Here's 30 degrees. Here's our 3.0 meters per second. We'll make this one x. And we'll make this one the y component. Watch this one, because this time we're going to find the x component using sine, because the x component is the opposite side. Sine 30 is equal to opposite over hypotenuse. X ends up being equal to 1.5 meters per second. And the y component is found by using the cosine function. Cosine 30 degrees is equal to y over 3.0. The y component ends up being equal to 2.59808 meters per second. I'm going to box that off, keep it to the side where it belongs. We'll do our x component and our y component. Pi is equal to Pf again. This time, object number 1 is moving only on the y-axis, so it has a momentum of 0, for the x component, that is. Object number 2 isn't moving at all, so it has a momentum of 0 on the x-axis. m1v1f plus m2v2f. Now, good news here, masses are all the same. They cancel each other out. 0 on the left-hand side, so it doesn't matter. V1F is not 3 meters per second. V1F is 1.5. It's the x component of that 3. We're going to make it negative because it's going to the left. Plus V2F. And V2F is going to work out to be, for the x component here, positive 1.5 meters per second. Then we do the y component. Once again, Pi is equal to Pf. This time, object number 1 has a y momentum, m1v1i. It has no, object number 2 has no y momentum because it's not moving, equals m1v1f plus m2v2f. And once again, good news. In every term that's not 0, m appears, the same value of m appears, so we can cross it off. V1i is 4.5 meters per second. V1f is not 3, rather V1f is 2.5. And it's upwards. Object number 1 is going upwards after the collision, so we'll make it positive 2.59808 plus V2f. Solve for V2f here, works out to be 1.90192 meters per second. Now it's time to combine them. We have an x component that is 1.5 and a y component that is 1.9 and a resultant that goes from start to finish. Do the Pythagorean theorem here. V works out to be 2.4 meters per second, and theta is the inverse tan of opposite over adjacent. Works out to be 52 degrees, and we're going to call that north of east because we're measuring the angle from the east, but yet we're going north from the east, or north of east. Now I'd like you to have a look at worksheet number 4, again, this time questions 7 and 8, to finish off that worksheet.